Good evening. Welcome to the video lecture on the topic Advantages of Digital Communication Systems. And it is a part of a series of video lectures on digital communications. And this is Jay Krishna, currently with Sri Vidyaniketan Engineering College, Tirupati. So the advantages of digital communication system over analog communication system is given here. So the first advantage is inexpensive digital circuits. So the inexpensive digital circuits, when a complete system is designed, so this is valid. So how means the discrete the components in digital circuits are not fixed, so not connected. So hence we can reuse the components, as well as a switching can be used where a same set of hardware can be used for multiple purposes, which is not possible in the case of analog communications. And privacy is preserved, so data encryption can be done so that a certain users can access the data and the remaining they cannot access the data. So likewise, the privacy can be preserved and different types of data can be matched, because the voice, video or data all will be converted into only binary sequence. Thereby we can match all the data and can transmit the formatted or multiplexed signal over a single communication link, which is difficult or not possible in the case of analog communication. And error correction as well as a detection is possible in digital communication system by using different channel encoding techniques like block codes, convolutional codes, cyclic codes and turbo codes. Error correction can be done, and which cannot be done in the case of analog communications. And still, the digital communication system has some disadvantages. Of them, the first one is larger bandwidth requirement. The second one is synchronization. The digital communication system requires large bandwidth. So let's see how. Let's consider a 5 kHz sinusoidal signal. In the case of analog communication, let's take amplitude modulation as an example, which requires a bandwidth of 10 kHz. Whereas the same 5 kHz, if it is converted into digital, let's see how much bandwidth is required. So first of all, the signal will be sampled at a minimum of Nyquist rate. So it is a 5 kHz signal, so it will be sampled at 10 kHz. So within 1 second, there will be 10,000 samples. And if we assume that each sample is represented using 8 bits, we will be getting 10 kilo into 8 bits, so resulting in 80 kbps. Though we cannot directly relate kilohertz and kbps, there is a certain relation between these two, and we can see that the requirement of bandwidth in the case of digital is too high. Noise immunity. So the noise immunity for digital communication system is very good, very high. Let's see how. So to elaborate on this, I'm showing the simulation. So let's take the amplitude modulation into the consideration. So here I am taking a time reference t 1 to 100 in steps of 0.01. Then I am defining message signal. So this is my message signal, am cos omega mt, and this is the carrier signal, and then this is the amplitude modulated signal. So here we have generated AM signal, and then so this is where I am adding some noise, adding the noise using additive white Gaussian noise predefined function in MATLAB, and then I am receiving the signal and I am performing demodulation by some sort, and then I am generating the demodulated signal. So this is where I am generating the demodulated signal, and then I am plotting all these signals, and then I am in this line. So this is the line where I am calculating the mean square error between the message and demodulated signal. So here when there is no noise, automatically the perfect reconstruction is possible. Now I'm executing it. Let's see what will be the result. So it is executing. Yeah, so this is the signal this is the output that was shown. So let's analyze the output. So this is the message signal. Okay, so this is the message signal and this is the aim signal and this is the transmitted signal. Maybe it should be the received signal after the channel effect, and this is the demodulated signal. So here we can observe that there is some sort of effect of noise. That's why the demodulated signal is not exactly equal to the message signal. Now let's see the mean square error which will be printed in the command window. So here we can see that there is a certain amount of mean square error. Now let's make the signal to noise ratio to be 1 and I am executing. So here, so now I am changing the signal to noise ratio to 10, and in this case if you observe, so the effect of noise is very less. Okay, the effect of noise is there but it is very less. And when we increase the signal to noise ratio, I am taking something like an ideal case. So in this case, let's see the waveform. Yeah, so here we got a perfect reconstruction. So the transmitted signal, received signal, so here the noise is very less. But when we reduce the signal to noise ratio to say something like -5, I have taken the signal to noise ratio to be -5. So in this case you observe, so this is the output which we got, and if you take -10, so the situation is becoming more worse, and even if we take -1, there is the effect of the channel, or there is effect of noise on the demodulated signal. Now let's take the case of digital modulation or digital communication system. For that I am taking a digital modulation technique called PSK as an example, phase shift keying. So let's see how we coded it. So I have taken a digital sequence, and so this is where, so this is the logic to generate the intermediate sequence, and then we are performing, yeah, so this is where we are performing the phase shift keying, and then we are performing the demodulation here, and then we are plotting the signal, and then we are calculating the mean square error. So here the noise is added after modulation. So let's go to that line. So here this is the noise. So I'm taking I'm taking as for an example 1, and I'm executing it. Yeah, this is the output. See, there is no error at all. This is the transmitted signal and this is the received signal. There is no error, and error is ultimately a 0. And if you compare in the case of analog modulation, when we have taken a signal to noise ratio of 1, there is a certain amount of effect of noise on the received signal, but in the case of digital communication there is no error at all. Now I am taking signal to noise ratio of -5. I hope you remember in the case of amplitude modulation, that is unlike communication system, when signal to noise ratio is -5, the effect of noise is very high, but in the case of digital communication, see the effect, there is no effect, completely no effect. So I am reducing the signal to noise ratio to -10 and I am inspecting, still there is no error. See, this is all because there is a decision device which is going to take the value during a particular time interval, either a 0 or 1. So even when there is an effect of noise continuously over the signal, the effect of noise is not directly affecting the information that we are processing, because we are taking only one of two levels in the case of digital communication, either a 0 or 1. So even when there is an effect of noise on the signal during all the values of time, the effect will be very less, because we are going to use a decision device which is going to give either a 0 or 1 based on the signal that we receive during that particular time interval. Okay, so now let's further increase the signal to noise ratio. I am taking it to we are reducing the signal to noise ratio to 25. Still there is no effect of noise, and I am making it -40, and let's see. So here is effect of noise. So here first of all 1 is received as 0, 0 is received as 1, then 0 is received as 0, 1 is received as 1, 1 is received as 1. The rest of the things okay. The first two bits are clearly affected by the noise. Okay, so this is happening at -40. So if we, for instance, if we take such a noise effect, that is -40 in the case of amplitude modulation, see the effect. See this is the message signal, and you observe the demodulated signal. This is completely different from message signal. Okay, so the effect of noise on digital communication is nominal, and it is very less compared to that of analog communication. Thank you.